Ewan Cassidy will speak of spectral caps for random Schreier graphs.
Okay, so thank you for the invitation to talk. Yeah, I'll be talking about spectral gaps for random Schreier graphs. So I'll start off by quickly recapping Friedman's theorem. So if we fix some integer r greater than 1, and we take GNR to be a connected 2R regular graph on n vertices. Okay, so then the adjacency matrix of GNR, AGNR, has n eigenvalues. Okay, the largest of which is equal to the degree of the graph. And then the rest are small. Okay, and we have a quantity here if and only if G is bipartite. Okay, so then we define lambda of GNR to be the largest non-trivial eigenvalue. So this is the trivial eigenvalue equal to the degree. So this is equal to maximum over all of the eigenvalues that are not equal to 2R. Okay, and then there's the Alomba-Panner bound, which says that this largest non-trivial eigenvalue is greater than or equal to 2R minus 1 minus little o of 1. Okay. So if you have a family of 2R regular graphs on n vertices, as the number of vertices n goes to infinity, this is the asymptotically optimal lower bound on your largest non-trivial eigenvalue. Okay, so families of graphs that have largest non-trivial eigenvalue that's sort of close to this lower bound, they have a near-optimal spectral gap. Okay, so what does Friedman's theorem say? This is from, I think it was published in 2008, that graph 2R regular graphs on n vertices having this near optimal spectral gap is actually typical behavior of these sort of graphs. So if we choose a random 2R regular graph on n vertices, then for any epsilon greater than 0, the probability that the second largest eigenvalue of GNR is within epsilon of this asymptotically optimal lower bound, this probability tends towards 1 as the number of vertices goes to infinity. Okay, so how do we choose a random 2R regular graph on n vertices? We use the permutation model. So we take GNR to be a Schreier graph. This is the graph associated to the action of Sn. symmetric group on the set of elements 1 to n, and we choose R permutations. Okay, so this is a graph, and it has vertex set n, so it has n vertices, and then we have an edge between any two vertices that are mapped to each other by one of these sigma. Okay, and if we take these to be uniformly random, then we get a random 2R regular graph on n vertices. So the question I sort of want to consider today is, call this formula star, is does star hold so does this new optimal spectral gap hold if we consider Schreier graphs for associated to the action of Sn on sets other than the set. So I'm going to swap n from set x. And in general, we're interested in sets that are strictly bigger than this set of numbers 1 to n. So maybe for some motivation for considering this question, consider random Cayley graphs. So if you consider a random Cayley graph of Sn with respect to some random generating set S, okay, where S has fixed size R and S is random. So it's an open question, I think it was mentioned in some previous talks this week, whether or not a random Cayley graph, a Cayley graph of Sn with a random generating set has a spectral gap, or has a uniform spectral gap, or if it has a near-optimal spectral gap. So by uniform, I just mean like less than or equal to some constant depending on CR. Okay, so it's an open question whether these random Cayley graphs have a uniform spectral gap with high probability, or if they have a near-optimal spectral gap with high probability. Okay, so it was shown by Kasabov that you can construct generating sets of a fixed size, so that these family of Cayley graphs have a uniform spectral gap. Whether this behavior is typical for random generating sets is unknown. But yeah, so what is this Cayley graph? This is just a special case of these Schreier graphs. This is just the Schreier graph associated to the action of Sn on itself by the left regular action with respect to the generating set S. Okay, and this is just the Schreier graph associated to the action of Sn on the set n sub n with respect to S, where I denote n sub k is k tuples of distinct elements. Okay, and then we have permutation acts on I1. It just acts diagonally on these k tuples. Okay. So if you have k equal to n, this is just n tuples of distinct elements and 1 to n. So if you have an n tuple, this is just the same as a permutation. So you get this. So this really is just the same as the k. So then this sort of motivates why we could consider sort of Schreier graphs associated to the action of Sn on k tuples maybe we could sort of obtain strong enough bounds that we can allow K to grow then. And so the idea would be to try and allow K to grow at the same rate as n, so have K equal to n. So I'll quickly go over what is known and what we proved here. So I mean, the difficulty here is if you have these Cayley graphs, you need to be able to say something about many more representations of irreducible representations of Sn, because you only get, as K grows, you get more representations appearing in the more irreducible representations is appearing in the representation associated to this action. Okay, so what is known here? So I'll now denote G, M, R, K is the Schreier graph. Sn acting on K tuples with respect to our random permutations. So for K equals 1, we know that star holds. Right, and this is just Friedman's theorem. So for K fixed, so it's proven quite a long time ago that G and RK have a uniform spectral gap. With high probability. So with probability tending to 1 as the number of vertices, as n goes to infinity, there's some constant here that you can bound the second largest eigenvalue of these Schreier graphs, and this is a result of Friedman, Zhu, Reuchmann, Stern, and Tillich from 1998. And then it was recently proven last year in their paper on sort of new approach to strong convergence that for fixed K we actually have a near optimal spectral gap. And this was proven by Chen, Garza-Vargas, Trop, and Van Andel. Okay, they proved this. They actually proved a stronger statement relating to strong convergence of random permutations in the representations associated to these actions. They proved this using this new polynomial method for strong convergence. So in particular, they give a short proof of Friedman's theorem, but they can extend this to proving these near optimal spectral graphs for any fixed K. Just that this, you can take this to be n. You can take the bound to be like as small as you like. So yeah, this is just saying there's a spectral graph. This is saying. Okay, but using this new polynomial method developed by Chen, Garza-Vargas, Trop, and Van Andel, and with some new group theoretic inputs, we're able to obtain strong enough quantitative bounds on this probability that we can grow K with n. We can actually grow K really rapidly with n. So star holds. So we have a near optimal spectral gap for these random regular Schreier graphs. For K now depending on n, we can actually locate polynomially with n. And just for context on this, if you have this statement for alpha equal to 1, you have this result for Cayley graph.
You have this simultaneously for all k in this regime?
Yeah.
Like all the
Could you please clarify that when you say we, you mean you?
Oh, yeah, I should have. Yeah, so we obtain this by giving a uniform probability value for all k, and then
I don't understand the statement. Is it able that it's a sequence to tend to infinity?
Yeah. Yeah, this is like this isn't written precisely, but yeah.
Every. Every?
Yeah.
Or so
For any
any
yeah. As long as it's less than or equal to n to this small power.
all the representations from this roll at the same time.
Yeah. Okay, so yeah, like I said, we prove this part 3 result where k is allowed to grow with n by taking the polynomial method developed to prove to part B, and we have some new sort of group theoretic inputs that allow us to get strong enough bounds that we can grow k with them. So maybe I just want to very briefly say something about that. So yeah, this polynomial method is actually a very general method used for proving strong convergence of in this setting of random permutations in the representations associated to these actions. So I just want to very briefly say something about strong convergence. So this is very rough. So roughly, if we have a set, a symmetric group acting on some set X, okay, this gives you a representation Ix of Sn. And so the adjacency matrix of the Schreier graph associated to this action is given by you sum over each of your permutations so the idea in proving these spectral gap results is you prove some sort of convergence of this polynomial in these permutations in this representation, and show that it converges to some limit. So strong convergence is asking for the same sort of convergence, but instead of taking this simple polynomial, you can take any non-commutative polynomial in these operators. Yeah, that's all I want to say about strong convergence. I think there's a couple of talks later in the week on this topic more directly. But yeah, so this polynomial method is used to prove not only the spectral gap results for the adjacency matrix, but they prove strong convergence for the representations associated to these actions of Sn on k-tuples. So maybe I should say something about what these representations are. So these are stable representations. So we fix k greater than or equal to 1. We take some Young diagram of size k. So for example, if we have lambda has this shape, then we define for n greater than or equal to 2k. We define lambda plus of n, which is a Young diagram of size n, and it has shape lambda outside the top row, and then you add a row of n minus k boxes, so this gives you a Young diagram of size n. Okay, and this corresponds to some irreducible representation. Which denotes rho lambda plus n. And these are the irreducible representations that appear for fixed k. These are the representations that appear in the representation associated to the action of Sn on k-tuples. We should say that these have dimension. So the dimension of these irreducible representations is just given by the trace for the character at the identity, and this is roughly a polynomial in n of degree k. So if degree the number of boxes outside the first row of the Young diagram. So for example, if we take k equal to 1, so there's only one choice for lambda here, lambda plus n. Rho lambda plus.
Sorry, I like your picture, but I didn't understand. What does your picture mean? Lambda equals to?
So you have some Young diagram lambda with k boxes. So for example, if you have this.
Oh, okay. Okay, so Young diagram.
Yeah. So then you just add n minus k boxes to the top row, and then you get a Young diagram of size n. Okay. Yeah. So for example, if you have k equal to 1, lambda is just one box.
Yeah.
So lambda plus of n is the Young diagram with one box, and then n minus 1 boxes, and this just corresponds to the standard representation of Sn. This has dimension. N minus 1. So strong convergence with strong convergence for this standard representation. So this is strong convergence for the representation associated to frequency. So you just have tuples of size 1. This was proven by Bordenave and Collins in 2019. And what Chen, Garza-Vargas, Trop, and Van Handel prove is you have strong convergence for all of these stable representations for any fixed k. Okay. So you have this you have this strong convergence for all these representations that have polynomial dimension. And And using some new inputs to this polynomial method, we can prove strong convergence for all representations whose dimension grows like quasi-exponentially in n, which is the representations associated to this action of Sn on Kn tuples. I should say that you don't necessarily need the full strength of this polynomial method to prove these spectral gap results. It's kind of overkill to prove strong convergence when you only need to prove convergence for this polynomial.
Sorry, I still don't understand the meaning of strong convergence. I mean, you have now, for any sigma, you have a sequence of representations, and you have the operators in each. So what convergence mean of I sigma itself or any polynomial?
So you have some collection of operators like pi x sigma 1, pi x sigma 1 inverse, up to pi x sigma r, and you just take any polynomial in these operators, and these converge in some sense to some limit, which I don't want to say too much on, but in the same sense that this polynomial converges to 2 root 2r minus 1. If you take any polynomial, these converge in some sense to some.
But the convergence is not in a limiting representation, like that. It's in the family of representation index by n. That's all.
Is convergence the norm for the regular representation?
Yeah.
Convergence is the norm for the regular representation?
Yeah, so converges, to the operator norm of the same polynomial in the three unitaries from the, So yeah, the point is to extend these results by Chen, Grasser, Vargas, Chop, and Van Handel. We have some new sort of group theoretic inputs to the polynomial method. So I want to say a bit about these. These new inputs are related to word measures in this object. So again, quite rough, but the polynomial method relies roughly on asymptotic expansions. So what do I mean by this? If we fix some word in the free group, now I'm doing this x1 dxi. And if we take phi n to be some map from the free group into Sn, just by choosing where to send each generator. Can we consider, we take the expectation over all choices of these sigma I, so all choices of these phi n. The expected trace in the representation you're interested in, so this is the trace in one of these stable representations of the image of W. Okay, so this just evaluates to some permutation. You look at the expected trace in the representation you're interested in of this permutation. Okay, so if here lambda is a Young diagram of size k, I'll call this star star. And so this has some asymptotic expansion that you can write like this. AK n to the k plus 2a1 times n plus some constant plus all these negative powers n. So in general, if you have a better asymptotic bound on this expansion, you can get stronger results out of this polynomial method. So that's the basic idea. So what are some examples? So for example, okay, so the first example is if your word is just the identity, you're just going to get the dimension out on this right-hand side. For example, if you take your word W to just be one of the generators, so you're then looking at the expected irreducible, non-trivial irreducible character of just a uniformly random permutation. And we know from character theory and Schreier orthogonality that this is just equal to 0. And in fact, we know exactly when this expression, in this case, is equal to 0. And this for a special family of words called primitive words. So then there's a result of a long time ago of Frobenius. And this says for any chi, so now we're not in the stable, thinking about stable representation, just saying for any irreducible representation chi of Sn. If your word is a commutator, okay, so you're looking at the expected character of the commutator of two uniformly random permutations. And this is just then this expected character is equal to 1 over the dimension. Okay, and again, this can be proved using character theory and orthogonality. So this sort of captures a lot of cancellation, so that for any representation, if you have a commutator, this expansion is 1 over the dimension. But more generally, there is a result of Nika from 94, where it's written more explicitly by lineal computer 2010. So for k equal to 1, so your stable irreducible representation here is just the standard representation. And so the character of the standard representation is just the number of fixed points minus 1. You get rid of the trivial representation that appears. And so what Nika shows is that if you have, okay, assuming your word is not the identity, if your word is not a power of some other word in the free group, then this expression star star is equal to big O 1 over n. So this is big O. Of 1 over the dimension of the representation. I should say for powers so if your word is a power of some other word with d greater than 1, this is O1. In this case, the implicit constant is just the number of divisors of the exponent. But you see there's, in general, even for words that aren't the commutator, you have some cancellation going on to get this asymptotic bound of big O of 1 over the dimension of the standard representation. In fact, this is the input used in the original paper on the polynomial method to reprove Friedman's theorem, and they use this big O of 1 over n for non-powers, big O of 1 for powers, to any. So if you take any stable representation, so k can be greater than 1, you still have these asymptotic bounds, and these follow from some results of Hanani and Kuda. And they use this as the input to prove their spectral gap result for fixed k of the random regular Schreier graphs. But yeah, so the general idea is if you have a better asymptotic bound on this expression, then you can get stronger results out of the polynomial method. And we're seeing that, okay, for commutators, for any character you have big O of 1 over the dimension. And for the standard representation, as long as your word's not a power, you have big O of 1 over the dimension. So maybe this sort of cancellation is sort of typical behavior for these stable representations. And it turns out that this is the case. So this is the new input that we prove to sort of feed into the polynomial method, and we get stronger results out of it. So this says for any k fixed greater than 1. And for any Young diagram of size k, if the word's not the identity and it's not a power of some other word, then when we look at this expected irreducible character of the image of this word in Sn, then we get big O of 1 over the dimension. And as I said before, yeah, these have dimension polynomial in n to the power of degree k. This is big O. In some sense, there's a lot of cancellation going on. Like you sort of expect randomness to give you some cancellation, but in this sense, you're sampling permutations in Sn, and you're pushing these into representations of dimension n to the k, and somehow you're still getting more cancellation. Your round gets better as that dimension gets bigger. So I'll say. So for k equal to 1, this is just the same as Nika. And for k equal to 1, stronger bounds. So for k equal to 1, this is the standard representation. So you can look at this character by counting fixed points minus 1. And for this in this case, stronger bounds are known, which are dependent on properties of your word W. And these stronger bounds are conjectured. For larger k. Yes, so asymptotic, yeah. So the conjecture is okay. So think in the standard representation, you have big O of 1 over n. But the results of Peter and Poznanszewski show that you can take this to some. You can take a higher power of n based on some property of the word called permittivity. And then these results are conjectured that you'd have n to the k to the power of. So, the time that's left, I want to kind of briefly give an idea of how to prove this sort of result in this setting. And this is using a method called combinatorial integration. So the first step is to sort of construct these representations you're interested in inside a nice representation of Sn. So you construct a space you might call U lambda inside C to the n tensor k. And U lambda has, if you look at the trace, so Sn acts on C to the n tensor k diagonally. And if you look at the trace in this representation, you just get some fixed multiple of the trace that you're interested in. So the next step is to construct explicitly the projection which I denote Q lambda, which projects from this space to the space you're interested in. These two steps can be done using sort of representation theory ideas and then Schreier duality. So then the point of doing this is that, okay, for each word in the free group, you want to look at this expectation over phi n of the trace in this irreducible representation. And this is just 1 over d lambda times the expected value of the trace in u lambda phi n of w. And this is just 1 over d lambda, the expected trace in c to the n tensor k of phi n of w, so this is just a permutation. You compose this with your projection. The point is that you can complete this expectation more straightforwardly because you're looking at a trace in c to the n tensor k. And so the trace in c to the n tensor k, you can just count standard basis vectors that are fixed by this operator. And this general idea of taking these expectations is a method called the Weingarten calculus. But in the case of Sn acting here, you can just count these standard basis vectors that are fixed. And the point is that when you have this representation constructed in the presence of this projector, you can see more cancellation than you wouldn't normally be able to see from this Weingarten calculus. And that gives you the bound here. So I think I've got time to quickly say. The proof to actually see this cancellation uses a seemingly unrelated result from sort of low-dimensional topology, which is called W cycles. So this is a result of Lauder and Wilton. So what does it say in this context? If you take some directed labeled graph G, and this is just a collection of circles that when you read them, when you traverse the circle, you read out some power of your word W. Okay, and you want the sum of the powers that you read out to be equal to k. So this has some natural covering map called delta just onto the graph W, which is just one W cycle. So each of these cycles sort of wraps around W. And then if you take any immersion of this graph G, which you call lambda, into some other graph gamma, or say gamma lambda, such that W is not a power. Every vertex in this gamma lambda is covered at least twice by this immersion. And the final condition is if you have two vertices in G, U1 and U2, the same vertex in W, so basically they represent the same point in your word. Then these have distinct images in gamma lambda. Okay, so then what does this result say? This says, if this is satisfied, then the Euler characteristic of gamma, so just the number of vertices minus the number of edges, is greater than or equal to k. Or you can show this is minus the Euler characteristic is less than or equal to minus k.
I don't understand condition 3. What if U1 is equal to U2? Still not.
Oh yeah, so you see. So if you say like, if you have two vertices that represent the start of your word, they'll map to, like say U1 here. Okay, and they map to the same vertex here. They have to have a different image, distinct image here.
Distinguish.
Yeah. And if you have these conditions satisfied, then the Euler characteristic of this graph is greater than or equal to k. And using these first few steps, we show that the expected value yn of a stable irreducible character this is bounded by the sum over all of the possible immersions lambda n to the minus chi. And the point is that the representation theoretic construction of U lambda in the presence of the projection allow you to show this bound, and then we can use this result of Lauder and Wilton to obtain our bound here. We actually, there is some small modification that we need to prove, where you don't quite have cycles, you have them like, they can be cut into just paths. But it doesn't really matter.
There's a sign there. So if I have next match the sign.
I put n to the minus.
As well with that. I said we never
Oh yeah, minus chi. Okay.
Yes.
Yeah. But yeah, the point is you can use these conditions in your construction of your representation to show that these conditions are satisfied, from which you get the bound. And then when you have a strong enough bound like this, you can put it into the polynomial method, and you can extract strong convergence results, which immediately imply some spectral gap results. Yeah, that's all I wanted to say, so thank you.
We have time for a couple of questions. So if there are any questions,
Can you describe this map delta again? So it's just, you have like an immersion of these W cycles into some graph gamma. You basically obtain this immersion by sort of gluing together vertices of these W cycles, and you can like merge edges together. And you have to do this in such a way that you never, if these two vertices have the same image in W, then you don't glue them, you can't glue them together, so they have to remain distinct. And yeah, when you think of, you take the sum over all the possible gluings so that this graph gamma that you obtain satisfies these conditions, then you can say that when the characteristic is small.
I had a question about the conjecture about bound that you stated. So your theorem says that the set of words for which the thing does not decay as 1 over n to the k, these are the proper powers. But what does the conjecture say? Say what are the words for which it doesn't decay as 1/10 to the 2k? Do you have a description of that? The conjectural description of that?
Yeah.
Or 3k? And would that be enough to show that the inductive function of these things is tempered in the sense that?
So the conjecture behind it is okay. So there's this thing called a primitivity rank of your word, which sort of quantifies how close your word is to one of the generators of the free group. So the conjecture is you have bigger of 1 compared to the k, and this primitivity rank is denoted pi of w, so you have pi of w is less than or equal to the number of generators. So depending on, so for example, if you take, there's known if you have w is equal to x1, x2, x3 squared. This has primitivity rank 3, so then with this you would expect bigger of 1/n to the 2k. But to applying the polynomial method, in some sense these proper powers are bad. So you need some knowledge of the sort of geometry of proper powers within the free group. So I don't know if you could immediately show that in this method that you have like temperedness, because you need some idea of the geometry of words of primitivity rank greater than or equal to 2.
It's false. It's even for the free group. Once you go to higher degrees, you're no longer tempered, and that's why you see these outliers. That's the tangles of Friedman come exactly from there. So
Okay.
they cannot be tempered.
Okay. Yeah.
It depends on if you do a Cayley graph, or like if you do just an Laplace that you're doing, it depends on the number of generators up to where they're tempered. So if you have 2 generators, then already the second order term is not tempered.
Yeah. And that's because if you have 2 generators, this is conjecture to be like
No, but I mean, you could now look at all the words of primitivity rank 2 or 3, right? And now ask how many words reduce to that, and then the exponential growth rate is larger than
okay. Yeah.
than you'd expect from the regulars.
Okay. Thank you.
All right. Thank you.